When we are dealing with antenna, one of the main parameters that we usually consider is radiation pattern. So in this video, we will explore what is meant by radiation pattern and why it is so important in our communication system, and what is meant by the azimuth pattern, elevation pattern, and why we are taking the dB values when considering the radiation pattern. So let's see. The radiation pattern of an antenna is defined as the mathematical or graphical representation of the radiation properties of the antenna as a function of space coordinate. So these radiation properties may be including the field strength, power distribution, polarization. So it shows how the power or the field distribution is happening across all the 3D coordinates system. So that is meant by the radiation pattern. So we usually measure or plot the radiation pattern in far field regions. Radiation pattern can be mainly divided into amplitude field pattern or amplitude power pattern. So this is the electric field distribution from an antenna. You can see the dependency on the two angles theta and phi. These are the spherical coordinates. And if we are plotting the magnitude of this electric field along the three-dimensional axis, it's called amplitude field pattern. And in case of a power pattern, if we are plotting the power distribution instead of the electric field distribution along the three axis, it's called amplitude power pattern. So the power pattern is related to the electric field and magnetic field distribution by this equation. So power pattern is proportional to half E cross H. And when we are plotting both amplitude and power pattern, we have to use the logarithmic scale or mainly in dB for the better visual effects. So I will explain why we have to use this why we have to use the decibels scale for the radiation pattern. So here I have taken a radiation pattern example, and here you can see that this is the electric field, that is the field pattern, and it is in linear scale. So here you can see how the field pattern in linear scale is looking. So here we can see that these side lobe levels are not that much visible. So instead of linear scale, if you are going to use the dB scale, decibel scale, you can see the visibility is enhanced. That's why we are always using dB scaling for the patterns. So here you can see that if going to use the linear scale again to show the relationship between electric field, magnetic field and power. So here you can see that value of the electric field is around maximum value, that is this red is around 25.7. So I'm going to check the magnetic field pattern. It is around 0.0682. So if we calculate that, that is, if I'm going to calculate 0.0682 into 25.7, that is E cross H divided by 2, it gives around 0.87. So this will be the power value. So I'm going to see what will be the power value. So I'm going to check. Then here you can see that it is showing 0.87. That this is how the electric field distribution, magnetic field distribution and power are related. So here also you can see if you are going to look the power distribution in linear scaling, the visibility is not okay. So to enhance the visibility, we can always use the dB scaling. That's why we are always using the dB scaling for the radiation patterns. So in most of the reports, instead of these electric field distribution or the power flow distribution, we will be plotting these gain or directivity that will be plotted in most of the papers. When we study about radiation pattern, we usually say azimuth and elevation pattern. So these are the cut plane radiation patterns. So what is the requirement of these 2D cut plane pattern when we have these 3D radiation pattern? Let's see why it is so important. Because in earlier days, we don't have these simulation tools like CST, HFSS, nothing like that. So everything has to be done on the basis of the measurements. So if we have to do the radiation pattern measurements in 3D, that is in the whole ranges, it will be very tiresome job and it may be taking lot of time. So in that case, it was defined like it is possible to do the measurements in some cut planes, and we can have the analysis based on that. That's why these 2D cut planes were evolved and defined at that time. So in the case of a azimuth pattern or elevation pattern, let's see what it is. So these are defined based on the electric field and magnetic field distribution. If we consider the case of a horn antenna, we know that this is the electric field distribution. So if this is my horn antenna and this is my Z direction, this is the Y direction, and this is the X direction, such that X is the direction of the propagation. So this means that my electric field is aligned in Z direction. So if I take a plane consisting of the electric field and the direction of the propagation, that is the direction of the electric field is in Z direction and the direction of propagation is along the X axis. So if we take that plane, that is the XZ plane, we call it as the E plane, and this is known as the elevation plane. So if I want to see the elevation plane in CST or software, if I'm considering a spherical coordinate system, here you can see the coordinates theta and phi. So if I have to take this elevation cut, what I can do is I can put phi equal to 0. That means I'll be able to cutting this radiation pattern along this green line. So this phi equal to 0 cut plane is known as the elevation plane, or in simple terms we can say it is just a vertical orientation, vertical direction. Similarly, when we consider the horn antenna, the magnetic field will be perpendicular to it, so it will be aligned along the y-axis, and H plane is the plane containing the magnetic field and the direction of the propagation. So this y x plane is the not YZ. YX plane is the horizontal cut, or it is known as the azimuth pattern. So if I want to get that value, I have to make theta to 90° and cut it here. So I'll be getting the azimuth pattern. So I can cut phi equal to 0. I'll be getting the vertical pattern or the elevation pattern. So here you can see how my elevation pattern will be looking. And if I can cut at theta equal to 90°, I'll be getting the horizontal pattern. That is that is how we are defining the azimuth and elevation pattern, and we will be usually measuring only this type of cuts, phi equal to 0 or theta equal to 90° cut plane. If your antenna is aligned in some other axis, this cut plane will be different, but you have to only consider this parameter. Like if you have to take an elevation pattern, it should be like something vertical, and if it is an azimuth, it has to be horizontal. So based on that, you can define the cut plane and take the radiation pattern. So I'm going to just show how it is. So this is the 3D radiation pattern. So if I have to get the vertical alignment, I have to cut along phi equal to 0. So I can go to the 1D, and for phi equal to 0, I'll be getting the pattern. And if I have to get the horizontal axis, I have to make theta equal to 90°. I can go to this one and I can make theta equal to 90°. So that will give me the horizontal pattern. This is how we are getting the horizontal and vertical pattern. So these are the different regions of radiation patterns. So if we consider the pattern in the 2D cut planes, it will be having the major lobe, minor lobe, side lobes, and back lobe. So major lobe is the lobe where most of the radiation will be concentrating, and the minor lobe is the minor lobes are the lobes except the major lobes. So anything, every lobes except the major lobe can be considered as the minor lobes. And side lobe will be near to the major lobe, and it will be on the same plane as the major lobe. So it will be in the same direction as the major lobe, and back lobe will be coming just opposite to the major lobe. So this is how it will be. So in our CST we can see how it is. So I have taken a cut plane here, cut plane pattern here. So this is the major lobe. So here you can see that maximum power is occurring at this point, and it can be given by 14.1 dB. That is the maximum power. And one thing is half power beam width. This is the beam width where the power is reduced to half of the maximum value. As it is 14.1, half of the power means it has to be reduced by 3 dB. So when it is reduced by 11.1, I have marked 2 points here. So this 2 and 3 represents where the power is reduced to half of the maximum value. Here you can see that value is occurring at minus 15° and 15°. So this is the half power beam width, and that value is also displayed here. So the 3D beam width is around 31.4, that is from -15 to +15. This is the half power beam width, and the full null beam width is where this major lobe is reduced to minimum value. So this is the first null occurring here, and the separation between these first two nulls is known as the full null bandwidth, and the and every other lobes except this major lobe is known as the side lobe, minor lobes, and the lobe which is near to the major lobe and within -90 degree to +90 degree, so this will be in the same direction as the major lobe, so this is known as the side lobe. So first minor lobe which will be in the same direction of this the main lobe is known as the side lobe, and the lobe which is opposite to the major lobe, so that means we have a major lobe at 0 degree, so the lobe at 180 degrees, so this peaks will corresponds to the back lobe. So this is how the radiation pattern is defined. We saw that we are getting lot of informations like side lobe level, minor lobe levels, back lobe levels informations from these radiation patterns. So these informations are very useful in deciding whether the designed antenna is useful for a specific applications or not, because these side lobe levels may be causing a lot of interference to the main lobe due to the reflections from these side lobe levels. So the radiation pattern forms an important parameter in designing the antennas. I hope you get some idea about what is meant by radiation pattern and what are these different cut planes, etc. So if you find any of these documents useful, kindly support and subscribe. Thank you.